things like viscosity, where we defined how does it affect. So in the last class, I might have we all did the conversion, right? How to convert a unit to favor our calculations in the. Wait, I'll do one thing. I'll share the screen. So we learned about some of the main fluid properties and how do they affect the fluid, that is either of solid, liquid or gas. Is my screen visible?
Yes, sir.
Yes.
Is my voice clear?
Yes, sir.
So yes, today we'll see about another fluid property, that is surface tension. So in the previous classes, we have learned or understood a bit about what is adhesive and cohesive forces. Cohesive force is nothing but force of attraction, that is the pulling force between two molecules of same substance. So these two are H2O molecules. The chemical composition is the same. So cohesion is defined as force of pulling or force of attraction between the molecules of a same substance. So addition, what does this mean? Force of attraction between the molecules of different substance. Here the wall is a solid form, whereas H2O is a liquid state molecule. So the force of attraction or the sticky nature between the wall and the closest water molecule. So all the water molecules, this is a glass. I have zoomed it. This is a microscopic or zoomed view inside a glass. So when I take two H2O molecules among several other H2O molecules, the molecules that are in contact with the wall of glass, those exhibit an adhesive or sticky property with the wall, while the inner molecules, it is a distant molecules away from the glass, what do? They exhibit a pulling force between the molecules of a same substance. So that is where your adhesive and cohesive forces exist. So coming to surface tension, due to the molecular attraction, liquids possess certain properties like cohesion, which means the intermolecular attraction or the pulling force between the molecules of same liquid or same substance, which enables. So what does this cohesive force create? It enables the liquid to resist any tensile stress. And adhesion. Adhesion means attraction between the molecules of liquid, one substance, and molecules of a solid boundary, that is another type of substance in contact with the liquid. So this adhesion causes sticky nature between the molecules of liquid with the solid boundary. So surface tension. So this is the objective here. It is caused by the force of cohesion at the free surface. Free surface means whatever surface. If you see the glass in this view, there will be a top level, right? The last top level, or if we see from the top view, whatever surface of the water is visible to us, the topmost layer of water surface is called the free surface. Surface tension is caused by the force of cohesion, because this particle, it will definitely, since it is pulling this one, so there might be some water molecule above this also, beside this, beneath this, side of this, so it exhibits a pulling force. So surface tension, what does it do? It just forms a free surface here. So since it gets pulled, so there will be a void formation here. So that is called surface tension, is called by the is caused by the force of cohesion, or the pulling force between the water molecules at the free surface, that is at the top surface. So let's see how the surface tension acts in different what you call the 3-4 conditions or different states. So first one is inside a liquid like water. Each molecule, that is each H2O molecule, is attracted by the molecules all around it. So the other molecules, they get cause a pulling force. They get pulled by each other molecules. A molecule at the surface of the liquid, that is the top surface, that is here, that is at the top surface, or whatever is visible from the top view, is however attracted by the molecules below it and beside it, but not above, because there will be no water molecules. Here, when you look at the top surface, there is obviously no water molecule here, but there will be the presence of water molecules beside, on the left and right, and beneath it. So whenever any water molecule gets attracted by such molecules beside or beneath it, this effect, pulling force, is called the surface tension. It's as if the surface wants to pull itself together. It is for this reason molecules of a water and soap bubbles, whenever you observe soap bubbles, why do they still, unless and until you, what you call, you exert some force or you blow away the soap bubbles with air, they remain to be in the shape of a sphere, because inter water molecules, they pull, the outer surface gets pulled by the inner forces. So that is why, unless and until we blow away the soap bubbles, they to the maximum extent try or stay in the shape of a sphere. So let's take some conditions. Suppose we now want to derive an equation for surface tension on a liquid droplet. We take an example of liquid droplet. So obviously, when I take some bowl and fill it with water, the topmost surface, what happens here? Whatever the molecules, water molecules present in the topmost surface, they have some pull, or they are pulled by the inner water molecules. So these inside water molecules, whatever they are present, they pull this top layer or topmost layer of water molecules. So obviously, what is happening? Tensile forces is acting. So let us consider that surface tension is of sigma. What do we know about sigma? How can we define it? Tensile force per length. So obviously your tension will be tensile force, that is the inner force that is acting over the circumference. This tensile force is somewhat a force which is acting from the outside. It is acting on the outermost or the circumference of the layer. So what does here it happen? For the liquid droplet to stay in equilibrium or to continue to stay as a liquid, the same droplet, it has to have some inner forces, right? It has to resist these forces. So these are called inner pressure forces. So here tensile force, whatever is acting, it is from the outside of the bubble onto the circumference, whole circumference of the liquid droplet. While a pressure force, that is the inner liquid, that is the virtue of its own forces. What do these do? It opposes. So, for a liquid droplet to be in equilibrium, the pressure force must be equal to the tensile force. So, that be equal as well as opposite. So, these two forces must be acting head to head. So, neither should pressure force be more nor should tensile force be more for a liquid droplet to be in equilibrium. So stress, when you take your strength of materials, I hope your strength of materials basics are covered. If not, your stress or force, let's say assume that we represent it by force, pressure, force. Stress equals to force per area. P, force equals to force of the inner bubbles by the whole area, that is area of circle. This pressure force acts on the entire area, while tensile force acts from outside only on the circumference. So what do you mean by it? P, pressure force, that is F, and tensile force is T. So stress equals to force by area. Surface tension equals to tensile force. Where is it acting? On the length, outer length of your outer circumference. Surface tension equals to tensile force per length, whereas your stress, stress equals to force acting on the whole circular liquid area. So here F should be equal to T. So what will T become here? Sigma into L, obviously. What is your L? Your L is the outer diameter. The tensile force is acting on the outer circumference. So obviously it is pi into outer diameter. F, what will F become here? P into area. So here you will have two pressures. One is outside atmospheric pressure and the other one is pressure inside the water bubbles. So it's not obvious that they both should be equal. Your atmospheric pressure on the outside will be lesser than your water pressure. Only then your liquid droplet will be equilibrium. So here when you need to become F equal to T, you'll obviously make sigma into L. Sigma into L. That is pi into the whole circumference, that is the diameter of the liquid droplet. Similarly, pressure force, that is F equals to P, that is you have to check for the change in the pressure from the outside atmosphere. So what will delta P be? P1, that is the inner bubble force, minus the atmospheric pressure, that is the atmospheric pressure that is existing around the liquid droplet. So this will be area of water bubble, that is pi by 4 into d square. So when you equate this both and by solving you get sigma p equals to 4 times of sigma by d. So surface tension acting on the whole diameter, d is almost 4 times. So this pressure, change in the pressure is 4 times of surface tension acting over the circumference. So that is about your surface tension on the liquid droplet. So when you take the next, sometimes in the question, they might not give you the delta P as a whole. They might give you P atmospheric pressure and P1. So then what we have to do? We have to calculate delta P from the formula of 4 sigma by D. When they give these both, what should we do? We should then calculate delta P, that is by the formula, and then add it to the atmospheric pressure. Finally, what do we get? That is the P1, pressure inside the bubble. So always this pressure must be more than the surrounding atmospheric pressure. Change in the pressure. So you will always subtract higher value from the lower value, right? So that is here. This is the condition when the droplet must be in equilibrium. Then we go for the second case. Suppose let us consider surface tension for a condition on a hollow bubble. So here we want to know the pressure change to keep the hollow bubble in equilibrium. So what do we have? Here we have surface tension. Here we have the pressure. So stress equals to force per area. Here the pressure force is acting on whole area of the bubble, right? So here always a hollow bubble will have two diameters. That is one outside diameter, a thin small film will separate your inner diameter also. It might be in mm. It is not visible to the naked eye, but hollow bubble will have two diameters. Though where we neglect the second film because it is very negligible. So stress equals to force per area, where your force by area. Area is we are subtracting the outer higher value minus the inner value. I'll give you the notes for this, don't worry. I'll forward you the derivation part. This is only for the class explanation. Even if you think that some terms are not visible, I'll share the PPT or the PDF. This is for class discussion only. Surface tension equals to tensile force acting on a phi d. That is, we have two surfaces here, right? So it is outer surface plus inner surface because your surface tension will be acting on a hole, that is on the both layers. So pi d plus pi d, that is 2 pi d. When we need to keep the hollow bubble in equilibrium, obviously these two forces must be equal and opposite. So what do we do here? F equal to T. So what do we take F as? P into pi by 4 of D square, because we are neglecting the smaller diameter, that is a thin film, equals to T means sigma into 2 into pi d. We are summing up both the diameters here. So when we solve it, we get P equals to 8 sigma by D. When they give us the atmospheric pressure, in the last condition, we have seen that this inside pressure of the bubble will be more than the outside atmospheric pressure. So change in the pressure, if sometimes they mention in the question, then we'll go for P minus P atmosphere. Pressure inside minus the atmospheric pressure present on outside the bubble. So in the case of hollow bubble, it is sigma P equals to, that is change in the pressure equals to 8 times of surface tension acting over the diameter or circumference of the water bubble. So here when it was liquid droplet, we got was only 4 times. Change in pressure was 4 times of surface tension acting over circumference. But for hollow bubble, we have 8 times. That is, it is almost twice. 8 times of surface tension acting over the circumference or the diameter of the hollow bubble. So in the next case, there is a third condition where we talk about liquid jet. That is any jet which is allowing the liquid to pass through it. This is the horizontal jet. This will allow water stored inside to flush, will push the water. So suppose we consider a liquid jet of length, height, which is L, and diameter, which is D. So when you immerse a liquid jet in water, what happens? The liquid phase or the water will be exerting pressure on this side and also this side. That is, both the faces of the liquid jet, water will be exerting some pressure. So here, what is the condition for liquid jet to be in equilibrium? Again, pressure force must be equal to tensile force. So here, stress equals to force into area. That is area L into D. While we go for tensile force, what it happens? Surface tension acting over both the faces. In the case of tensile force, since the diameter is very small, we neglect here. So we sum up 2L, that is water exerting the pressure on both the sides with both diameters, that is the whole perimeter of the liquid jet, that is 2 into L plus D perimeter. We neglect the D shear because the liquid jets D will be very small, so it will not show, it might not show any such effect that will cause a major difference in the value. So sigma into 2 times of L, that is the perimeter of the liquid jet, which is 2 into L plus D, where we ignore D. So what happens here? P or F equals to T. So P, pressure, force into area, that is length, height into diameter. So we are covering the entire area, equals to surface tension into the water force exerting on the perimeter, that is sigma into 2L. So when we need P, that is 2 into sigma by D. So in some cases, we also go for the change in the pressure is acting on twice amount of surface tension acting over the diameter of the liquid jet. So in this case, it is half. The liquid droplet, it was 4 times of surface tension acting over the diameter. In this case, it is half, that is it decreased. So it is 2 sigma by D. It's better if you note these formulas. Even though I'll be sharing the PDF version with you, it's better if you note down these formulas. First one is surface tension on a liquid droplet, where you draw these figures for your understanding, and then I'll share the slides with you for you to prepare the notes. So for a liquid droplet, always remember change in the pressure will be 4 times the surface tension acting over the diameter of the liquid droplet. In the case of hollow bubble, to be in equilibrium, change in pressure is equals to 8 times of surface tension acting over the diameter of the hollow bubble. In the case of liquid jet, change in pressure is 2 times of surface tension by diameter of the liquid jet. So we have a small problem here. Let's do a small exercise. Here we have been given P1 and P2. So obviously here we have been given the delta P itself. So we did not find P1, P2. Directly we have been given a change in pressure, that is 0.02 Newton per centimeter square at a temperature of 20 degrees. Surface tension acting is 0.0725 Newton per meter. Change in pressure they have given. Initially, what is change in pressure? Pressure of the inner bubbles minus the pressure of the surrounding air, or atmospheric pressure is 0.02 Newton per centimeter square. We have to find D. So for liquid droplet, the first formula, that is change in pressure equals to 4 sigma by d. Here sigma we have in Newton per meter, while delta P we have it in Newton per centimeter square. So instead of reducing this meter into centimeter, it will be better, easier calculation to reduce this centimeter to into meter. So this value will be further decreased. So what do we get here? 1 centimeter, 1 meter equals to 100 centimeters. It is 10 power minus 4, right? So 0.02 by 10 power minus 4 equals to 4 into sigma, that is 0.0725 Newton per meter by d we need to calculate. So when we calculate the formula, it will become 0.001. So the main thing here is we are not worried more about the answer. If you do the calculation, it will come. But we are more worried about the terms here. Since it is delta P is given automatically, we did not again specifically calculate P1 and P2. This is one condition. When I go to a second type of example, for a case of soap bubble, so we have been given D, it is 40 mm. So it's better that we convert it into meters. The data also, the problem data has also specified that change in pressure is 2.5 Newton per mm square. So delta P is given, D is given. So we have to find sigma. In the case of soap bubble, hollow soap bubble, 8 sigma by D, that is the second formula. So change in pressure is specified. So we need not separately calculate or worry about calculating P1 and P. So formula is delta P equals to change in pressure equals to 8 times surface tension acting over the D. So we substitute the formula. D we have already reduced from millimeter to meters. So 0.04, 1 meter equals to 1000 mm, right? So we calculate the sigma by taking these both terms on the other side. So we have done in the case of liquid droplet, where we need to find the D. In this case, we were asked to find out the soap bubble. We have been given the data of D and delta P. Let's take a third condition. Here, the given data, we have been given atmospheric pressure. Atmospheric pressure equals to 10.32 Newton per centimeter square. So here we take the first formula, that is liquid droplet. We have been given the case of liquid droplet here. They'll definitely given the question what case it is. Either is a liquid droplet or soap bubble or liquid jet. Here for example, I have directly taken the data and illustrating the terms. So in the first case, sigma P, here we have been given P atmosphere, that is 10.32. So we need to calculate the P1. So delta P we can calculate using the formula of 4 sigma by D. What is delta P actually? P1 minus subtracting from the surrounding atmosphere. So when we get 4 sigma by D, we equate it to this P1 minus P atmosphere. We have P atmosphere. We will be solving 4 sigma by D. We will be getting the value of P1. So sigma. We have been given the question that sigma is, for example, 0.0725 Newton per meter. So 1 meter is 100 centimeters. So we reduce this surface tension value into Newton per centimeters, because D and P atmosphere already have centimeter square. So instead of keeping it the same and changing these both, for our convenience, we change the sigma value itself because the other dimensions suit it. So we reduce it and convert it into Newton per centimeter. So we have P atmosphere value. We will calculate 4 sigma by D. So delta P, that is P1 minus P atmosphere, substituting the equation 4 into sigma. We have reduced the value from meter to centimeter by D, that is 0.04, reducing from mm to centimeter. So we get this value first here solving, and then we know the value of P atmosphere given in the question. So P1 we have to find out. So P1 minus P atmosphere is 10.32. Dimensions are units are same. So equals to the value of this 4 sigma by T. So P1, taking this on the other side, adding, we get the required answer in centimeter centimeter square. So this is about your 3 conditions. So I'll again share the standard PDF with you. These are some examples. We'll again work out in the coming sessions in detail. This was the basic questions. So mostly you keep concentration, or our concern is how do we deduce. So these two equations are the primary basic equations. So from that we take force equal to T, tensile force. So this condition is the crucial one along with this basics. So for getting F and T, we multiply P into A. Here sigma into this equation. Thus we equate, because for droplet to be in equilibrium, always pressure force, inner pressure force inside must be equal and opposite to the tensile force acting from the outside onto the bubble or liquid jet, or the first case liquid droplet. So here don't forget we neglect, because we assume that diameter is small. So we, while calculating the perimeter, we take in terms of L only, because L is the major axis here. D is the minor axis. We assume that diameter is small. So these examples, once again, you look at it. I'll share the PDF or PPT. If you have doubts, you please ask me. So coming to the next property, that is capillarity. Wait a minute. Yes. So surface tension. What did we see in surface tension? I'll just get back. Surface tension was due to the force of cohesion, that is force of attraction between the same molecules. Here while capillary action, it is due to the both cohesion as well as adhesion. So water molecules will be pulling other water molecules beside or beneath them, and also water molecules get sticked to the tube or to the wall of the tube. So here we are taking 2 examples. We will describe capillarity. Initial definition is it is due to the both cohesion as well as adhesion. We'll explain it in 2 terms. One is with water, one is with mercury. So here our object is two objects of water and mercury. So what happens in the first case? If a glass tube of a small diameter is partially immersed, so we only immerse half, what you call height of the glass tube. We don't submerge it fully. We only make it half immersed. So if a glass tube of a small diameter is partially immersed in the water will wet the surface of tube. What is happening here? Water is wetting the surface of tube. So it is adhesive force, because whatever the water molecules near the wall, they are sticking. Thus, what will happen? Since more water molecules stick here, obviously there will be more water molecules attracting towards the wall of the tube rather than in the center. So here adhesion or your adhesive force is dominating the cohesive force. In the case of water, when at the point of contact of the wall with the water molecules. So what will happen? Since it is more, the water is being attracted towards the wall. Obviously, the water level will rise than the outside water level. So the inner water level, due to this sticky nature, more water molecules will be attracted towards the end of this wall tube. So the water level falls here, obviously it will be rising or getting attracted towards the wall. This is called a concave shape upward. When you have like this, it is concave downward. In the case of mercury, here it is concave shape upward. Here obviously adhesion property is the dominating property over cohesion. So liquid is wetting solid. That is obviously happening here. Water molecules, it is getting sticked to the glass tube. So obviously liquid is wetting the solid boundary. So thus here the water level rises than the normal water level. So here the subject is sticking to the tube wall or coming, attracting towards the tube of the wall. Thus, liquid wet the solid surface. Well, in the case of mercury, the same glass tube is now partially immersed in the mercury. What will happen? Mercury, it will not wet. It is having more cohesion. That is the pulling force. So the force of attraction between the molecules of same substance is more than the molecules of different substances. In this case, water was getting attracted towards the wall. In this case, water is getting pulled away from the glass tube intermolecular attraction force. So obviously mercury level will be decreasing here. So when it stops getting into contact, what happens? The mercury level gets depressed. So all this water comes around here. So the natural water level will be more outside. While in the case of liquid, it was rise. It had a rise, concave upward. While here, the level of mercury will get depressed. So here there will be rise during the contact with water, while in this case you will get a fall or the depression occurs in the case of mercury. So cohesion is dominating. That is the force of attraction between the molecules of same substance is getting dominated over the sticky substance. It is dominating. So the liquid surface or the mercury containing surface depresses or there is a fall in the height, initial height. So it is concave downwards. So here what happens happening? Rather than particles getting attracted to the tube wall, particles, intermolecular particles form a bond. That is, they come close to one another. They pull the desired molecule. So that is about your surface tension, the conditions and capillarity. So yes, I'll wait a minute. Screen में अलग लगाते तो yes, there was some disturbance in the middle. Yes, this was the disturbance. So we described about surface tension and capillarity. So it is all about the cohesion and adhesion. Now we will discuss about vapor pressure. So we'll stop here after discussing the vapor pressure. If it doesn't stop today, I will continue to explain tomorrow and I will revise in case it is a working day tomorrow. Vapor pressure is nothing or it is defined as the ability of particles, that is the inner property of particles to escape from the liquid. It is a pressure characteristic. So what is happening here? The ability of particles to escape from the liquid, that is the liquid molecules are getting excited. So they try to escape towards or away towards the top, away from the existing water surface. It is a pressure characteristic. So we take an example of a liquid kept in a closed vessel. This is the example of liquid kept in the closed vessel. What happens? Definitely vaporization takes place. Thus, the vapor molecules they come up, they escape the surface of the water and they occupy whatever the free surface. So before it was empty here. So whenever the closed vessel condition occurs, the liquid molecules escape from the water surface and they form a and they fill or they occupy the free surface till the top of vessel. So whatever space it is, they occupy. This accumulated vapor. So definitely when they are here, it is in the state of liquid. When they come up out of the liquid surface, they are no more liquid. They are in the form of steam or vapor. So the state of matter here has changed from here. These accumulated vapor exerts pressure, exerts vertical downward pressure on the liquid surface, that is the top surface. This is called vapor pressure. Thus, change of state from liquid state to gaseous state. This is called vaporization. When all the liquids have some vapor pressure, that is Vp, it is a strong function of temperature. Therefore, some liquids have significant, that is higher vapor pressure at the room temperature, that is at the normal temperature, while other liquids might not. Liquids with a significant or greater vapor pressure at room temperature or general temperature are called volatile. This means they will evaporate fastly, that is these liquid molecules will escape from the surface, converting into a state of gases or steam or vapor molecules within hours or days. It is in a short time they will rise up to evaporate or to escape from the liquid surface rather than weeks or months. So this is about your vapor pressure. It is all about the pressure caused of these molecules over the liquid surface. So the change from this liquid state to the gaseous state is called vaporization. So yes, I think I'll stop the topic at here today. So tomorrow, in case there is a working day, those who have missed some previous sessions due to network connection, they can come tomorrow, attend tomorrow, so that I will revise the entire topic from starting to today's session. That is all the till now discussed fluid properties. So I'll stop presenting here. Sirisha, attendance తీసుకున్నావమ్మా?
సార్
22 మెంబర్ 23 మెంబర్స్ వచ్చారు ఈరోజు.
లేదు సార్ 27 ఇందాకలా మధ్యలో క్లాస్ మధ్యలో వెళ్ళిపోయి ఉంటారు.
Okay. Hmm. So I hope today's session was a bit easier to understand. I'll share the PDFs in detailed form and we'll also work out some examples, some more examples, or I'll share the detailed workload problems to you soon so that you'll get more practice. So if you still have any issues, you can share those in the chat box. If you still have any issues that require improvement from my side, please share those in the chat box.
సార్ గూగుల్ ఫామ్
Emma,